Thank you for coming today. Today's talk is about GPS tracking and what do you do with information collected from GPS. Our speaker today is John Crum from Microsoft Research. John graduated from CMU in 1993 with PhD in robotics, and he worked in the robotics center in SNL for 4 years in object detection and I think individuals inside car detections. And then he joined Microsoft Research in 1997. And since then, he was working in location determination, location-based services. He worked in many systems, actually. Smart MoveX, which is RF-based location determination, Locadio, which is based on radio signal strengths, and Spot, which is based on FM signal strengths. So without any further introduction, I introduce John. Thank you for coming, John.
Thanks, Adele. So the reason I know Adele is he was a summer intern of mine at Microsoft a few years ago, one of my favorite ones, and I was going to be down here, and I got in contact with him, and I said, I just want to see if you really have free lunches here, and so he said he's going to take me to a free lunch after my talk, so we'll see if it's really true. So I said that this is not really part of the main outline of my talk, but I said that Adele was a summer intern with me, and I just want to tell you what he worked on and what he did. Microsoft had this product, we still do, called the Spot Watch, which gets actual updates on weather and dining and traffic and movies over sidebands of commercial FM radio stations. And the Spot team came to us and said, could you make that watch location aware? It's got this FM tuner in it. We can tune to any FM station and measure how strong the signal strengths are. So what Adele did, he did a really nice job and wrote this paper on making that watch actually location aware. So it kind of knows where it is, just based on measuring signal strengths from commercial FM radio stations. So that was a cool thing.
That actually works in production?
No, it's not in the product.
So, I mean, does it have a database of where all the ground stations are? Or?
Basically, what it does is it looks at fingerprints, how as a function of latitude, longitude, what are the set of signal strengths that you're going to see. So that's the database it's based on.
Where the function is?
No, it actually doesn't. You do war driving beforehand to get the ground truth. So what I'm going to talk about the rest of my talk is projects that we've been doing on top of some GPS data that we've been collecting. So we went out and we bought 55 of these Garmin GPS receivers, and we're loaning them out to volunteer drivers to leave on the dashboard of their car for 2 weeks or 4 weeks at a time. They record up to 10,000 time-stamped latitude longitudes, and so far we've had 227 people go through the program, 1.77 million points, and 12,500 separate trips. And down below there you can see what some of the data looks like. So these are mostly all Microsoft employees, so they're all usually around the Seattle area. In fact, that's Microsoft right there, so it's particularly dense there. And when we started with these GPS receivers, we didn't really know exactly what we were going to do with them. But since then, we've thought of some research projects on top of them, so I'm going to talk about those. And the first one is destination modeling. What we have here, these are destinations of people in our study. So what we do is we segment the GPS into discrete trips, and the last lat long of each trip is the destination of that trip. And we looked at, well, what can we say about people's destinations? One thing is we can look at the types of places they seem to like to go. So the map on the right there is a U.S. Geological Survey map of the Seattle area, where each 30 meter by 30 meter square on the ground is categorized into one of 21 different ground cover types. And what we did is we looked at the type of ground cover that people tend to like to go to. And it turned out that commercial and low intensity residential are the most popular ones. And kind of as you'd expect, emergent herbaceous wetlands and woody wetlands, which I think is another word for swamp, basically, are not really all that popular as destinations. And then a little later on, I'll show how we actually use this to do something useful.
Does the fact that high intensity residential shows up so low, does that indicate that it didn't get a signal there? Or?
Let's see. Oh yeah, this one here. That's a good point. Yeah, maybe that's what happened. because that's where the urban canyons would be and things like that.
Yeah, I'm surprised
Yep.
it has that much in the forest areas, considering how poorly GPS usually does when there's a lot of trees around.
Right, yeah, yeah. We also looked at how people behave as a function of time. So this top plot here, it's as a function of a 24-hour clock, and here are the number of trips per week that people make as versus the time of the day. So there are not too many trips in the middle of the night. You see quite a few here in the morning, maybe people commuting to work. And down here in the evening, maybe people are going home or going out to restaurants like that. So this kind of makes sense. Then you can also look at how many of these trips are trips to new destinations that we haven't observed the person to go to before. And that peaks right around the middle of the day. You can also look at how those things vary as the day of the week. So that's what we have over here, the days of the week. And here are the number of trips taken per week. And so it turns out the most trips are taken on Thursday. And I'm not really sure why that would be. And then you can look at number of new trips, places to new destinations where the person hasn't been before. And that peaks kind of as you'd expect on Saturday when people might be going off to trying new things. But it's also pretty high here on Thursday. And then finally, on this destination modeling thing, we looked at how fast do people generally kind of fall into a rut of not visiting new destinations at all. So we, in general, when we first gave the people a GPS, they visited a little over 3.5 destinations. And then we looked at how many destinations they visited on the second day that they hadn't visited on the first day, and it's down here a little over 1.5, and it goes down exponentially kind of like that. So people fall into a rut sort of, after about 2 weeks, they've come fairly close to hitting steady state. We also have demographics on all these people. So we're interested in, does this rate of decay vary with the demographic makeup of the people who are in the study? And we found no difference between single people and people with a partner, children versus no children, extended family nearby or not. There was no significant difference, but we did find a small but statistically significant difference between men and women. And women's rate of decay is slightly higher than men's, or they go down and hit the steady state a little bit faster.
I have a question.
Yeah.
In this sample, were there people driving as well as like public transportation and that?
This is all pretty much driving because they just put it on the dashboard of their car. Yeah.
On what day of the week were the GPS units issued to people?
It
Curious if it was Thursday.
no, it's totally random. We just sent them out via the mail. So whatever day they get there.
Would the bias of new trips, especially every trip's a new trip when you first get it, was that accounted for?
No, we didn't account for that. We knew that the starting dates were all random, so we were kind of hoping the randomness would average out to general behavior. But you're right. If like Saturday was the second day here, then you probably wouldn't see quite the same behavior. Yeah. So I don't know why that women decline a little bit faster than men, and I don't want to speculate on it either. So the next project was one called Predestination. And this is where we're trying to predict where you're driving to as you drive. So you get in your car, start on a trip, and can we predict when you're going to stop and get out of your car? And the reason why you'd ever want to do that is one is anticipatory information. If you could warn someone of an upcoming traffic jam before they get there, that would be useful. And of course, you can get traffic incident data, but you can only get it in a radius of where you are around a certain point. And if we could actually tell you that you're coming up on something, but not tell you about the things that you've left behind, then that's less distraction for the driver. Location-based advertising is another one. No one wants to hear about a sale on bananas as you drive 40 miles an hour by a grocery store. But if, at least in the Seattle area, we've got these third-party parking lots around the airport. So if 10 minutes before I got to the airport, I could get an ad that said there's a discount on parking at some place, then I actually have time to act on that ad, and I might actually welcome it. And then finally, this is kind of an interesting application for hybrid vehicles. The way most hybrid vehicles work, they have a gas engine that can charge up a battery. And the vehicle has to decide when to turn on the gas engine to do some charging. So if a car is coming up a hill, say, it might find that the battery's a little bit low and say, well, I guess I need to turn on the gas engine to charge the battery at this point. But if the car knew that it was going to have a good charging opportunity by going down a long hill, then it wouldn't necessarily have to turn on the gas engine before it gets to the top. And so it could be made more efficient that way. So our basic approach to this, to predicting where you're driving, is we split up the region into 1 kilometer cells, and we compute a probability for each one of those cells as to whether or not that's your destination. And then, you know, that's just regular old discrete probability distribution where they all have to sum to 1. And so now we get back to that ground cover model that I was talking about. So that's the same bar graph over here. And if you apply those normalized probabilities to the ground covers that are actually inside those 1 kilometer cells, then this is the prior probability distribution that you get. And you can see that, you know, probability of ending in a lake is pretty low, which is good. And also rural areas are pretty low. This is a rural area out here, but you do see some little pops here by these little towns on these rural areas. So this kind of makes sense. We also looked at prior on personal destinations. So the easiest way to predict where someone is going is to look at the places that they've been before. And so here are the destinations of some of the people, or one person in our study. So those cells would have a higher probability. We also looked at something to try to make this work a little better out of the box. So each image here is a 40 pixel by 40 pixel image, where each pixel corresponds to one of those cells. And on day 1, this person visited these cells, day 2, these, and on down to day 14. So you can see how the destinations for this person evolved over time. Now, if we're doing predictions for day 2 based on day 1, we're never going to get that destination up there because the person hasn't visited it before. So we wanted to try to account for the fact that out of the box, this isn't necessarily going to work all that well. So what we did is we tried to anticipate what the probability distribution would be on this day based on just the days that we've observed. And we noticed 2 things, that new destinations sometimes sparkle, so they'll just pop up where there wasn't anyone before and not nearby any other ones. And they also tend to cluster, so you can see some clusters of destinations in through here. So what we do is we add a little bit of background probability to account for that, that sparkling. And then we also we blur the destinations a little bit with a wedding cake model like this, which tends to model that clustering. And as time goes on, this is the effect of the background and that wedding cake model. They drop down to 0 because the steady state is being approached. So after about 2 weeks here again, we're almost at steady state. So this red line means that we're really paying attention to just the places that the person has actually gone and not trying to modify the probability distributions anymore. The third thing we looked at for predicting where we're going, and then these all get glommed together at the end, is efficient driving. And what we're trying to model here is the fact that if you're driving along here, say, and you head north, chances are that you're not going any place south, like this. And so what we did is we looked at the trips that people are actually taking and kind of learned how efficient most drivers are. And they're not 100% efficient getting to their destination, but they're fairly efficient. So for a candidate destination, you know, one of those squares, we could say if the person has passed up a lot of opportunities for an efficient route to that cell, then the probability of that cell has to be pretty low. And so here's how that looks. Here's a person who started a trip and they've gone 4 squares south. We've recomputed the probabilities just based on efficient driving, and you see this basically upper triangle has been eliminated. Here where a darker outline means a higher probability. And they continue their trip down here, and now the only probabilities that are really non-zero are down here. So that's doing a reasonable job, it seems like. Then finally, a very simple one, we look at trip times. You know, you get in your car here, and you're probably not going to drive to Chicago. You're probably driving, you know, between 0 or 40 minutes or something like that. So that just tends to bound how far away the destinations are. And I'll skip the math here, but this is just to say that we put this all together in a Bayesian probability framework, so it's all mathematically principled, and we didn't have to come up with how much we're going to weight the different components and things like that. It just all fell out of the math nicely. And the result looks like this, and this is the line to look at here. This is the fraction of the trip that's been completed, and this is the median error in predicting the cell that you're going to stop in, where we just take the highest probability cell as the one we think you're going to stop in. So the error goes down as a function of time, as you'd expect, And at the halfway point, our median error is about 2 kilometers in predicting where you're going. So another project that we did was, oh yes.
How did you determine when a driver was stopping, or that was the destination?
Yeah, that involved segmenting the GPS data, and that's something that we don't know how to do all that well. But what we did is we looked for gaps of greater than 5 minutes in the data, and then we had to eliminate some little short garbage trips when we did that. But yeah, we just looked for 5-minute gaps.
Okay, so they weren't instructed to like push a button for start versus stop.
That's right. Yeah, the way the GPSs are, we had to modify them a little bit, but they just set them on the dashboard of their car, plug them into the cigarette lighter, and then just forget about them for the whole 2 weeks. They don't have to touch them again.
Well, if it's plugged in the cigarette lighter, then you could tell from the voltage whether the engine's running or not.
I guess you could if the GPS could measure that, but it doesn't. Some car cigarette lighters, it turns on, stay on when the key's off, and some come on.
I know, but it'll drop to just the battery voltage, whereas when the engine's running, it goes up because it's the alternator voltage.
Oh, I see. Okay. Yeah. All right. For the next project I want to talk about, it requires this as a prerequisite, and this is snapping to a road, which was deceptively hard problem, it turns out. What we have all this GPS data, and we need to know which road the person was actually driving on. And the most common way to solve this problem is just to snap the GPS to the nearest road. But that causes a disaster sometime. So for example, here we've got these 3 GPS points, 1, 2, and 3. And what we want the output of the program to be is the fact that you were driving on this road here, even though this GPS point didn't fall on a road or even that close to it, and it fell fairly close to some other roads as well. If you just do a nearest road snapping, you get a problem. Here are 3 GPS points connected by this black line, 1, 2, and 3. And if you just do snap to nearest road, that one snaps correctly, that one snapped correctly. This one here, instead of snapping to the east-west road, snapped to the north-south road. And what happened is the algorithm then fills in the roads that didn't have a GPS point. So it reasons that, well, if you were on this north-south road and next year over here, you would have had to drive north to the first U-turn opportunity, turn around, come back down, and get over here, okay? So the snap to nearest road, when you do the fill-in, fails like that. And so what we did is, instead of looking at just the locations of the GPS points, we looked at the timestamps as well. So point number 1 here, this is just a pretend scenario, snapped here. Point number 2 snaps here. And the question is, where does point number 3 snap? Should it snap over here or over to there instead? If you just do nearest road, then it ought to snap here. But what we can also do is we can just run a little routing algorithm and predict how long it would take to drive from here to here, or how long it would take to drive from here over to there. We can see which one of those times best matches the timestamps that we actually got from the GPS data.
Can't you guys just use like heading that's published with the GPS feed to sort of correct for this kind of?
That would be another good clue. Our GPSs actually don't record that though, so we just have the timestamp lat long altitude. Yep.
Doesn't most commercial software already do this, including Microsoft's? I think it's called Streets and Trips. I mean, how recent is this research?
Well, this is pretty recent, and what makes it slightly different from like the nav system in your car. The nav system in your car uses odometry and a compass as well as the GPS data. Yeah.
Do you have the speed as well as the position in the data you're using?
No. Of course, you could
you
kind of get that.
Receivers do record that. I don't know if these particular ones.
Yeah, these are really simple, so they don't record that. Yeah. Yep.
So what's the frequency at which the GPS points were recorded? Did it depend on just the time or even the delta from the last recorded point?
We put them in an adaptive recording mode, so we wouldn't fill up the memory. So if you're on a long straightaway going at a constant speed, it won't record that many points. But if you're weaving around a lot, then it records more.
Oh.
The average time between points was 6 seconds or 60 meters. Yeah. So we have to weight those two errors. How far can we snap in distance, and how far can we snap in time? Basically, how much can we ignore what the time to the planned route was? So we actually computed some statistics, assumed that the spatial error of GPS was Gaussian, came out to about 7.6 meters. And we looked at the error in our route planner. So when you're planning these little short routes, what's the error between the estimated time and the actual time to drive between these points? And that was a Gaussian that looks kind of like this. So now we could weight those two errors when we're trying to find the optimal route. This ends up just being a hidden Markov model, where this is the same thing that's used in speech processing, because in speech, when someone's talking along, it's pretty easy to anticipate what they're going to say next. So it's kind of like this. In this case, is we've got these noisy GPS measurements, and we have to anticipate what road the person is driving on next. So the hidden Markov model just looks at a whole bunch of different possible road snaps for every point in time, like this, and then picks the optimal path through these road snaps using the Viterbi algorithm that minimizes both the error in space and time. So an example kind of looks like this. Here, point 1 can match to here, here, or here, and GPS point number 2 can match to here, here, or here. So there are 3 possibilities over here, 4 possibilities over there. So there are 12 possible little short routes between these two. So we actually give those to our route planner and ask it, well, how long would it take to drive those 12 different routes? And then how does the timing of those routes, the duration, compare to the actual time it took? And then we do the optimal snap. So point 3 over here might have 3 different snaps, so then you've got 3 times 4 times 3. And the Viterbi algorithm in the hidden Markov model is just really good at efficiently finding the best way through that minimizes those errors. Yep.
If there's a traffic jam or something, do you start assuming they went really far away and came back?
You could, yeah, because that's a great point, because our router doesn't know about traffic jams. So it's just assuming clear traffic. So, yep.
You can actually take look at more points, right, in history and like 10 points in the past and 10 points in the future, and that will give you a much better estimate.
Well, yeah. So this algorithm is
That's not isolated within 1 or 2 points.
Right. Well, this algorithm is actually looking at all the points on the trip from beginning to end. So it's kind of a non-causal model because it's looking to the future as well. Yeah. So here's one of the results. The black again are the measured GPS points, just to connect the dots. This point here on the nearest road snapping, for some reason, snapped to the road down below. This point snapped to the correct road, but so nearest road snapping said, well, if you were here, or if you were on this highway under here and then ended up over here, what you'd have to do is turn around, come back, take the nearest entrance to the highway, get on, pick up that snapped point, and now the next snap point is over here, so I have to keep going, get off the highway, come back around here, over here, and now pick up that snapped point. But our algorithm cuts through, so it ignores that big excursion. And then we just looked at a lot of different examples of where our algorithm works and the nearest doesn't work. So here's a GPS problem. This point gets snapped here, so the nearest road gets pulled over there, but our algorithm doesn't. Distractions with crossovers, like the bridge I was just talking about. Parallel roads, sometimes the point would get snapped over the center median into the oncoming lane of traffic. Our algorithm doesn't fall for that trick. Distractions that are just little spurs off the road like this. Cutting through spaghetti intersections like this. The gray is the nearest road snapping algorithm, and the white is our algorithm. Passing around spaghetti intersections. Looping through spaghetti. So, in here there are just a lot of different choices for which road you can be on. Okay, so the reason we did that is we wanted to do this next project on personalized routes, and this is something that I did with another summer intern, Julie Lechner from the University of Washington. And what she was looking at is, when you go to a website now and ask for directions between 2 points, you can ask for the shortest route or the fastest route. But you can't ask for a route that, say, sticks to the roads that you tend to like to drive on. And what Julie found is we looked at the routes that people actually took in our data, and 60% of the people were taking neither the fastest nor the shortest routes between 2 points. So because these people live in the area, we assume that they were familiar with where they were driving. So they must have had some other reason to pick the routes that they were picking. In fact, here are 4 different routes between this point and this point. There's the empirically fastest that paid attention to traffic. There's the plan we got from map point, the shortest distance route, and the driver's route, and all 4 of those are different from each other. So what we did is we looked at 2 ways of making the routes better, hopefully to better match what people actually did. One was to look at traffic, So we could use all our GPS data just as traffic probes for each little section of road to see how fast traffic was moving on there. And we split those up as a function of 15-minute segments over the time of the day. So given the time of day that you wanted to make the trip, we could anticipate what traffic would be at that time. And so here's an example of someone who, this is just a regular commuter who starts his trip here and ends here. At midnight, he sticks to the highway like this. But during rush hour, he has a trick, and he goes off the highway for as long as he can and then gets on down here. The other thing we did, which is the more interesting part, I think, was we looked at the roads that each person drove on, and we would deflate the cost of those roads a little bit. So, so when you submit the route planning problem to your A-star search or your Dijkstra search, it looks at the cost of the roads, and we could say multiply the cost of the roads that you'd already driven on by 0.9 or something. So they're a little bit cheaper, and the router would tend to prefer those instead. And so we tested this on 2,500 trips from our GPS data, and we found that close to 47% of the personalized trips match the actual routes that people took, and that was quite a bit better than what we were getting from just using a standard router. So I think that was pretty successful in making the router more personalized. The last thing I want to talk about is location privacy. And the motivation here is there are a lot of reasons to send your latitude, longitude to a third party. One of those is congestion pricing, so toll roads, but like all roads can be a toll road, and you just get charged at the end of the month for which roads you happen to be driving on and when you were driving on them. Location-based services, we all know about. Pay-as-you-drive insurance, so your insurance rates vary depending on where and when you drive. This is an interesting device, this Dash, which was just announced recently. It's a navigation system that you can put on your dashboard, and it can give you real-time traffic updates. But where it gets the updates from is other drivers who are driving around. If they encounter some slow traffic, their GPS data is continually getting sent into a central server, which is looking for these traffic slowdowns based on this GPS data. And then it can instantly broadcast to the other people who have these systems. And then finally, research purposes. So a bunch of people ran around London with GPSs and made this map just by walking around. But those are all reasons that you might want to send your data off to a third party. And people say that, well, even if this data is anonymized, which is what, like for instance, the Dash system uses, everyone has this theory. Well, if someone knew where you go, they could easily figure out who you are just by figuring out where your home is, and then from that they could figure out your identity. And everyone's got this theory, but no one has tested it up to now. So we were able to actually test it. So we start off with these pseudonymized GPS tracks. That's just the proper term for anonymizing something, but replacing the name with a unique ID. Then we infer the home location of the people, and then we do a reverse white pages lookup to see if we can get their identity back. And so we had 4 simple algorithms for trying to infer where this person lives based on the GPS data. And the first of these 4 was called the last destination algorithm, and we segmented all our trips, all our data into discrete trips, and we looked at, for every day, we look at the last destination the person went to before 3 in the morning. And we took the median of all those for every day that we observed the person, and we assumed that that is the location of their home. And that was accurate down to about 61 meters median error.
Well, AOL demonstrated a somewhat similar concept a few months ago.
Who did?
AOL.
Oh, right. Exactly.
Data.
Yeah, yeah. Another algorithm, we called the weighted median algorithm. We didn't have to segment the data for this. We just looked at all the GPS points, and we computed the median of all the GPS points for a particular person, but the median was weighted by the amount of time that you spent at that particular location. That had an error of about 67 meters. We looked at a clustering algorithm where we just clustered all the destinations that a person had. We clustered up to, I think, till the cluster size got to about 100 meters in diameter. And we then just took the cluster that had the most points in it, figuring that your most frequent destination is home. And the median error here was about 67 meters, so the same as the previous one. Then finally we looked at this one involving probabilities. And this is the most principled of the four, but it's the one that works by far the worst. We looked at, since we know the home addresses of all the people in our study, I mean, by the way, that's how we can figure out what the error in this home finding algorithm is. So we've got all their home addresses. So what we did is we computed the relative probability that you're at home as a function of time of day. So this is a 24-hour clock along the bottom here. And this is relative probability that you'll be found at home. So you can see it starts to drop here at 8 a.m., kind of like you'd expect. So this is sort of like the number of trips, the complement of the number of trips you take as a function of the time of day. Goes down here, it's lower during the middle of the day, and then starts to rise here around 6 p.m. again. And so what the algorithm does is it looks at, for every person, it tries to find if there's a GPS point in the highest probability bin, and if it is, then it says, okay, that must be where they live. If there's not one in that bin, then it looks at the next highest probability and on down the line like that.
How do you calculate this probability?
We just, how do we calculate the probabilities? It's, we would just look at, for any given time of day, look at all the GPS points in that 1 hour bin and see if any of those points were at the home location of the person. And so just kind of relative frequency of being at home or not. Yeah. But this worked terribly, over 2 meters median error. And I think the reason it didn't work very well is that we actually don't have much data from when people are from the middle of the night like this, because our GPSs are set up in this adaptive recording mode, so when the car is parked, they don't record any data. And that's just to save memory. So if you had a different GPS receiver that was recording all the time, then this would probably work better.
But if you know that, then couldn't you say, look, I've got a point at this time, I've got a point at this time, and so presumably the receiver was just sitting there for that entire time?
Yeah, you probably could. That would be a good thing to do. So why wasn't this more accurate? Well, so our GPS recording interval, 6 seconds and 63 meters, so you could be fairly far away from your home before you get a GPS reading. GPS satellite acquisition takes a little bit of time. When you just start up the car and the GPS turns on, it can take about 45 seconds before you get the first reading from a satellite. Most GPSs have a cold start time kind of like that. And so you can drive 300 meters if you're going 50 miles an hour in that 45 seconds, so you can be pretty far away from your home. A lot of people have covered parking, so you don't get a GPS signal there, and a lot of people park far from their home. They have to park far from their home. So the GPS in the car is not necessarily a good proxy for where the person actually lives. So the next step was to, now that we had the home location down to about, I think 61 meters was the best we could do, was to see, could we do a reverse white pages lookup to get the identity of the person. And so, just like you guys, we have this API into our search, and one component of it is a white pages lookup. So this is just a little program I wrote that lets you click somewhere on the map, and it gives you the name, address, and phone number of the person who lives there, just based on their latitude and longitude. And it's not just because of where I work I have access to this, but anyone can download the API and could do this too. So you wouldn't have to be an evil genius necessarily to do this. Anyone could do it. And so here's how well it worked. Here's our attack. So we started off with GPS tracks of 172 people. We got their home location down to about 61 meters. We'd actually get the identity, the actual name, the correct name of the person with 5% of those. So this is kind of low. I thought it would be higher. And part of the reason is we're not getting the home locations all that accurately, but part of the reason is that reverse geocoding doesn't really work all that well, so given a lat long to get the house number is not necessarily all that accurate. And also the white pages are somewhat out of date. Some of this data is kind of old, so we didn't try the attack as soon as we got the fresh data from a person. We let it accumulate for like a year and a half, so some people moved away. Also, some people live in multi-unit buildings, like a condo or an apartment, so you're really not going to get what apartment number or what condo number they live in. And so we also looked at, well, what if we were dissatisfied in getting their home address, which kind of gets around the problem of, is the white pages up to date? And we could actually get the home address of 12% of the people in the study. So the first lesson from this is that everyone's theorized about these attacks, but the attacks actually work. So there is a problem. Even if the data is anonymized, someone can actually get your identity. And we kind of all thought that before, but now we know it's true. we were in a position to look at some countermeasures now for protecting your identity from someone doing an attack like this. And so a lot of people have written papers on this, how to protect your identity, and they propose different ways of doing it. Of course, they haven't been able to test them, so now we're able to test them. And one of the ways that they talk about is corrupting the data. So for instance here, this is some of the original data in our study. That's where the person lives. And here is Gaussian noise added to the GPS data with 50 meters standard deviation. So it looks like that. And then, so the question is, now if we run this noised data through the same algorithms that we ran before, how does it affect the algorithm? And what we did is we looked at, as a function of the amount of noise you add to the data, that's the standard deviation in meters, how many correct home address inferences do you get? And these are just using those 4 different algorithms that I talked about. So that's why there are 4 different bars for each number. And as you'd expect, the number goes down the more noise you add. But out here, you're adding 5 kilometers of noise standard deviation to the signal before you've really reduced the threat to almost 0.
To counteract this, I mean, you can maybe do some sort of clustering or something like that, right? If you are using Gaussian noise,
right,
to do this, maybe someone can do the reverse, maybe run some clustering algorithm locally.
Oh, right, yeah.
Run some filters, Kalman filters or anything like that too.
Sure. Yeah, I think, in general, if the attacker knows how you were trying to protect the data, then the attacker can figure out how to undo that. So if they know it's a simple thing like adding Gaussian noise, then there's a lot of statistics out there to help you with that. So you're right. Yep.
Maybe you have to add cryptographic noise.
Maybe. Yeah. Yep. So another technique you can try that's similar is just discretizing the data. So it's just coarser. And so there's the original data again. And here is just each point is snapped to a point on a grid where the grid points are 50 meters apart. So the data ends up looking like that at the end. So here's the same kind of plot as a function of the coarseness of this grid, how far apart these points are. And as you'd expect, the number does go down the more coarse you make the grid, but you've got to get out here to a grid where the points are 2 kilometers apart before you've really reduced to almost 0 the effect of the attack.
Does the functionality drop proportional to this also, in the sense that the actual algorithms for figuring out where you're going, do they drop as badly as this if you discretize or add noise?
Yeah, so that's a good question. Kind of the general question is, if you're trying to use these techniques for location-based services, how much does it affect the usefulness of the service? For instance, predicting where you're going or things like that. And that's something that we didn't look at all, and I think that would be a very interesting thing to look at next. Let's see. So for some things, like if you just want a weather report, right? Yeah, you don't really care if you're a couple kilometers off because the weather's not going to change. But if you want to know next time you get to a cheap gas station or something, then it's important to be fairly accurate. And then the final algorithm that we looked at for protecting you is just cloaking the data. So we delete the data in a circle that's near the person's home. And specifically what we do is we draw a small circle around the person's home. That's this circle here. And pick a random point inside that circle. And then around that random point, we draw a bigger circle and delete all the data inside that big circle. And the reason that we've got the randomness in there is if you centered this cloaking disk on the actual home, then it would be pretty easy for an attacker to figure that out and say, oh, okay, well, had to be at the middle of this place where all the data's missing.
That's what they call a void in CSI.
Okay, yeah, void. And so here's how that worked. Here's how many correct home addresses we got as a function of the radius of that little circle, the radius of the big circle. The little circle radius didn't have that much of an effect on the algorithm, but the big circle had to be about 1 kilometer in radius before the effect of the attack was almost 0. So the lesson here on this privacy part is that yes, that attack really does work, even though the data is anonymized. We all kind of knew that, but we verified it. But the other thing is that some of these proposed techniques for protecting you from an attack like this are not very good because you have to corrupt the data so much that it's really probably not going to be good for a lot of location-based services that you might be wanting to try.
Unless you do that processing locally where you're not worried about it.
Yeah, if you're not sending the data off your device to a central server, then right. Yep. Okay, so that's the end of my talk. I talked about our gathering of GPS data, the driver models, including a part that was based on places that you tend to like to go as a function of the ground cover. Our predestination algorithm, which gets your location down to about, your destination down to about 2 meters or 2 kilometers at the halfway point of the trip. A new algorithm for doing map matching, personalized routing that pays attention to the roads you tend to like to drive on, and then location privacy. So that's the end of my talk, and thanks for listening.